Hey, what's up everybody? This tutorial is going to cover confidence intervals for a difference in two proportions. So I'm going to run through the four-step process and then do an example at the end using the four steps. So four-step process, step one, you're going to define your parameters of interest. So you'll have two parameters this time, two population proportions. So you want to define those in step one. Step two is you have your conditions. So we need our random condition. You have two samples this time, so you need to have both samples being random. It'll usually tell you that in the prompt of the problem. We then need to check for a normal sampling distribution. So we actually have four conditions that we need to check. So four of these numbers, n1 times p hat 1, n1 times 1 minus p hat 1, n2 times p hat 2, and n2 times 1 minus p hat 2. All four of those numbers need to be greater than or equal to 10. If so, then that will satisfy your normal sampling distribution condition. And then, of course, you need your third condition for independence. Since most of the time your sampling will be done without replacement, it's important that your samples be no more than 10% of their population. So both samples need to meet that condition. Once those conditions are met, I usually name my procedure. I usually shorten this one to the z interval for p1 minus p2. All right, step three then, you actually calculate the interval. So the confidence interval consists basically of three things. So this will be your point estimate of your difference. So it's the difference of your two sample proportions. Then you got plus or minus your critical z-score. That's going to come from your confidence level. And I usually use my inverse norm calculator function on the TI calculator to get my critical z-score. And then this is your estimate of the standard error. I usually notate that as sigma sub p hat 1 minus p hat 2. So that will be your estimate of your standard error. And then step four, you do your interpretation. I kind of use this as a template. I am X% confident, so 95, 98, whatever your confidence level is. So I'm 95% confident that the interval blank to blank captures the difference between the true proportion of interest of population 1 and the true proportion of interest of population 2. So once you have a context, you want to put that into context. All right, so let's start an example. So I'll read through it, and then we'll start working through the steps below it. So Time Magazine reported the result of random telephone polls of adult American non-smokers and smokers. The question posed of the Americans who were surveyed was, should the federal tax on cigarettes be raised to pay for healthcare reform? The results of the survey for those who said yes were non-smokers. So that sample was 605, so I'm going to call that N1. The sample proportion was rounded to 0.58, so about 58% of the non-smokers sample said yes to that question. Then for the smokers sample, we had 195 smokers that were sampled. P hat 2 was 0.21, so 21% of the smokers sample said yes to that question. All right, so then the question then asks us to estimate the difference in the proportion of non-smokers and the proportion of smokers who support an increase in the cigarette tax. And we're going to use a 95% confidence interval here. All right, so let's start running through the four-step process. So step one, I need to define my parameters of interest. So I have two of them here. So P1 is going to be the true proportion of, and this is going to be of my non-smokers who support the tax increase. Okay, and then P2 So as my second parameter that I'm interested in is going to be the true proportion of smokers who support the tax increase. So what I'm interested in doing is trying to estimate the difference between these two parameters. All right, so that's step one, just defining your two parameters. All right, step two, now we want to verify our conditions. So remember, we want random samples. So if we look back at the problem prompt, it does say it reported the result of random telephone polls. So that will meet that condition. So we'll say 2 random samples. Check. Now we need to check for a normal sampling distribution. So this is where we need to go through these 4 calculations here. So we'll start doing that. So N1 times P hat 1 is 605 times 0.58, which is 350.9. That is greater than 10. We want N1 times 1 minus P hat 1. And that's 605 times 1 minus 0.58. And that will be 254.1, also greater than 10. So the first sample is good. Moving then to the second sample, N2 times P hat 2, 195 times 0.21. That's 40.95, which is greater than 10. And N2 minus times 1 minus P hat 2. 195 times 1 minus 0.21. And that's 154.05. Also greater than 10. So we can see that all of these numbers are greater than 10. So we are justified using that normal distribution. One thing to note here, usually these 4 numbers are going to be whole numbers. They're not whole numbers in this example because it's likely that the sample proportions, the 0.58 and the 0.21 were rounded values. But usually these 4 numbers should be whole numbers. Okay, so then the last condition is that we want our samples to be no more than 10% of their populations. So one way I think about that is if I take my 2 sample sizes and multiply them by 10, if it's reasonable to conclude that the population is more than the sample size times 10, that condition will be met. So if I take the 605, right, multiply that by 10, that's 6,050. If we're talking about American non-smokers, obviously the population is way higher than that. Do the same thing with smokers, it'd be 1,950. That population is also much greater than that number. So that third condition is met. So I'll say it is reasonable to conclude that each sample is no more than 10% of its population. Okay, so that independence condition is met. All right, then what I usually do then at the end of step 2 is now I'm going to name my procedure. So I'll say the conditions for a Z interval for P1 minus P2 Okay, so now I'm on to step 3. So step 3 now, I'm going to go ahead and use that formula that I have listed up here. So p hat 1 minus p hat 2 plus or minus critical z-score times my standard error. So I'll start kind of plugging in the numbers for that. So my difference in my sample proportions, 0.58 minus 0.21. And now it's going to be plus or minus my critical z-score. So my critical z-score for 95% confidence can be calculated using the inverse norm calculator function. So inverse norm, you have to put in the tail probability of the confidence level in for the first argument. So if it's a 95% confidence, you have a 0.025 tail probability. So if you put that into inverse norm, it's going to give you a critical z value of 1.96. So that goes in that position after that plus or minus sign. And then we have our big standard error formula. So it's going to be 0.58 times 1 minus 0.58 over 605. And then plus 0.21 times 1 minus 0.21 over 195. Okay, so I got all that plugged into my formula. And this difference is 0.37 plus or minus. And then basically, if I put all of this into my calculator, that's going to give me a margin of error of 0.69. So just about a 7 percentage point margin of error for this confidence interval. So then what I can do is then kind of put it into that interval notation. So if I subtract, I get 0.301, and if I add, I get 0.439. So that's going to be my confidence interval. So that would be my estimate for the difference in those two population parameters. So right around 30% up to about 44% would be that difference. I'm also going to show you this quick on the TI calculator. So what I'm going to do is I'm going to go to the stat menu, over to tests, and I'm going to scroll down until I hit 1 prop z int. So it's, excuse me, 2 prop z int. So you have 2 proportions, and then you're doing a z interval. So I'm going to click on that, and then it's going to ask me for x1, n1, x2, n2, and a confidence level. So the n values should be pretty obvious. So I'm going to go ahead and type those in, 605 and 195. The x value is what you divide by n to get your p hat values. So what you can do is if you just take the n value times the p hat value, and you can just do it right in this screen here, and hit enter, it's going to give you that 350.9. That's the same number that we got in step 2. Now, since the sample proportions were rounded, the calculator can accept an x value that's not a whole number. So what I'm going to do is I'm just going to round that up to 351. If you don't do that rounding, it will give you an error. And I'm going to do the same thing here. So 195 times 0.21, hit enter, and I'm going to round that 40.95 up to 41. All right, and then I'm going to go down to calculate. Right, and that'll give me that same interval that I calculated. The rounding's a little bit different, but that's a kind of a quick way, so you don't have to actually go and use the formula. Okay, so that is step 3. Now I'm going to move to step 4, where I do my interpretation. So again, if I just use that template that I have here for step 4, just putting it in context, that's going to look like something like this. I am 95% confident. The interval .301 to .439. captures the difference in the true proportion, let's say true proportions of non-smokers and smokers who favor the tax increase. Okay, so that's it. That's step 4, which kind of rounds out your 4-step process. So that is, again, the 4 steps that you're going to use for doing the z interval for P1 minus P2. All right, thanks for watching.